Let's begin lecture. Sorry, we had some technical difficulties up here with my with my laptop. I updated to Mac OS 10.15, which is Catalina, and I inadvertently messed up my display. I had all kinds of different colors and stuff. It's not perfect yet, but it's usable. I want to talk about exam 2, which is next Wednesday. So let's talk about that for a few minutes. First thing that I want to remind everybody is that since the grades are so low on exam 1, in our grading system, there's a lot of leeway with midterms because we keep the best 2 and drop the lowest. Right? So a student brought Chick-fil-A nuggets or those sliders.
Let me get one. Solid.
See, I was having a bad day already. And now,
Just shoot me an email on camera.
just kidding. But it did draw my attention immediately. Anyway, we have best 2 out of 3, and that's if you take all 3, and most of you will be in that category. And just so you, so exam 1 this semester may be the one you drop, and you may, the way, and I'm going to be writing exam 2 a little bit differently, okay? And I haven't written it yet, and I haven't decided how to write it, but I know it's gonna be different, and so you may do a lot better on exam 2 and exam 3 and stuff. So exam 1 might be the one that you drop. Now the reason I bring that up is to allow you not to panic, right? And I believe I've mentioned it before in lecture. So don't panic about your grades yet. If you're still crashing and burning after exam 2, then maybe it'll be time to, think about your options to withdraw or something like that. Question? I'm not sure yet. The question was, will I have clicker response questions at the end? Shh. Let me get to that in a minute. Okay, I'll answer that question in a second. The other thing I want to mention about the best 2 out of 3, for most of my classes, whether it's 2054 or astronomy 2002 or physical science 1120, anything that I teach, in which I have best 2 out of 3 midterms, it usually is exam 1 that is the dropped exam for a lot of students, sometimes the majority of the students. So, and I'll tell you, from observing you guys and from observing all my other classes, students get really nervous about exam 1 simply because they've never had an exam with me before and they don't know exactly what to expect. You now know what to expect, right? It's going to be challenging, but I don't want it to be so challenging that it would cause Andrew to cry up here, which I could easily do with multiple choice questions alone and high stakes. And this is high stakes for everybody. And I know that a lot of you are thinking, oh man, my GPA for grad school, my GPA for med school, MCATs and all that stuff. Yeah, I understand what a lot of you guys are worried about for that. And I think it's normal. But don't worry too much about it so that you paralyze yourself. Because for most of my classes, it's exam 1 that gets dropped. But for some students, it just happens to be exam 2. Some it happens to be exam 3. But for a lot of the students, I'd say that the most commonly dropped exam is exam 1. All right, now, what's going to be on the exam? It's going to be similar in format, except for the last page. All right, now the last page, the clicker page, where we had we had a couple multiple choice. And I can move multiple choice questions into the Scantron part. That's not a problem. The calculations, I can either keep as clicking questions, all right, or, especially for people that get here late, I can have a written problem solution page. All right. So on the written problem solution page, and the problem with giving you that, I would like to do that, and I may do that. I haven't decided yet. The problem is I haven't given any written problem homeworks yet. And usually I like to have at least a sprinkling of how I grade your written homeworks before you go in on a exam with a written problem that I grade, because I'll be grading most of them. All right, a packet of 100 papers uh, compared to some of my classes is a walk in the park. So I'll be grading it. If I give you a written problem, I might give you two written problems. You know, front one problem, and the back of the page another problem, and I'll let Andrew grade one of them, the easy one, and then I'll grade the tougher one for partial credit. You know, so I may do that, or I may continue with the eye clickers. Another thing that I'm going to do is more time. Okay, so, and I think that in-class review last time was not so hot. All right, because for a lot of reasons. The biggest reason was that a lot of people were getting discombobulated on the review going into writing the exam, and that's a bad mental state to be in when you're going into the exam. Now you make, you know, so what I'm saying is few of you would have had total disaster on exam one if we hadn't done that review. In my view, I'm not sure, but that's what I think. So I'm not gonna have an in-class review. We're gonna have more time, and but the thing that is going to be the same is the first 4 or 5 questions or so will be matching for formulas. Okay, and then we may have some true false. We also maybe have some multiple choice, and then we'll have either the clicking page for calculations, and or a written page for written problem solving. Okay. Now, if I give you the written problem solving, I'm trying to think of how to. Trying to think of how to phrase it. You're going to have to. You're going to have to write your written problem as a communication to me. Okay. Now, when you guys do your homework, you know, I was just working. I don't know who it was, Mackenzie. She's not here today. I was working with a student during office hours on Wednesday, and we dug out her scratch paper from the exam, and it was really hard for us to reconstruct what her thoughts were, because she made mistakes, and we were trying to see, what mistake did you make to get the wrong answer, and it was really hard because she just had numbers everywhere. Few equations. She didn't have any explanation of what she was doing. Now it was scratch work, so she didn't have to. But if you have a written problem on exam 2, and I'll try to announce it Monday. I'll let you know Monday if we're going to, either way, clicking questions or written. But if you have written, you're going to want to include a strategic sentence or two, a few phrases, and also it's going to have to be neat, and it's going to have to be legible. Now, I'm not familiar with your guys' handwriting, but if you have bad handwriting, I will mark you down if I can't read it. It absolutely has to be. And the reason I insist on that is if you're in a professional situation and you're communicating with your BOSS, he's got to be able to read it. It's got to be legible. And some of you are shooting to become MDs, And you know, MDs have this fable, this old wives' tale that they get their they have perfect handwriting going into med school, but by the time they get a job as a doctor writing prescriptions, their handwriting is illegible. That is a lie. It's deliberate. Yeah. So, anyways, so prescriptions aside, if you're in a situation where you have a job, I know that's a four-letter word for many of you, but you know, with a BOSS, you're going to have to talk to your boss, and sometimes written, sometimes verbal, and you're going to have to make it count. So, so, so handing me a written problem solution with numbers everywhere is not going to cut it. I'll mark it, I'll rip it apart. I'm really hard on written problems. Okay, you've got to have it. In some ways, I'm generous and abundant in mercy. If I can see you're barking up the right tree or something like that, but you're not, you miss a minus sign somewhere, something like that. But if you got numbers everywhere, that's it. I can't make heads or tails if it's wrong, especially if the answer is wrong. So I'll be looking for that on a written problem, and I can't do that on a clicking problem. I can give you maybe some partial credit on clicking if I can spot a common error numerically, but other than that, I can't. Daniel. Yeah, that's a good point. You know what I can do? I can post, and it'll be a nice little review of Physics 1. I will post, matter of fact, I'll just do it anyways. Tonight or tomorrow, I will post a set of 3 or 4 problem solutions from my Physics 1 exams in spring. And those will be my solutions. Now, I'm not going to post another, I have PDFs of student solutions, but I won't do that because you're not allowed to do that. But I will post my solutions, and you shall see how I grade, how I write the problem. And here's the other thing. On my problems, you've got to put it all on one piece of paper on that front side. That's all you get. You can't go over onto, scratch paper or anything. So you can have scratch paper and work stuff on the side, but your written problem that you turn in is going to have to be on that one side of the paper. And maybe maybe problem number 2 that Andrew grades will be on that side of the paper, and no overflow. And I'll grade it down if there's overflow. All right, so we got it. It's going to be, but I'll try to post a few examples in web courses. It's a little historical archive of dangerousness from the past. All right, another question. Yes, Andrew. Yes, I do, because I'm going to be looking for I'm going to be looking for your thinking. See, the reason that boy, I don't see everybody listening to me. I see people on their phones and stuff. Don't don't mess around with phones when I'm talking. This is serious. I'm sympathetic if you crash and burn on an exam, but not after I'm telling you about how the next exam is going to be. If you're not listening now and you crash and burn, God bless you. You had your shot. You could have listened on Friday before the exam. So the question was, if you have the right answer, is that all you're going to look at? And the answer is no, I'm not. I'm going to look at what you are thinking. That is why you want to think of it as a communication, right? And so that way it's going to be different from iClicker. iClicker, I just want that number, and sometimes I can detect a factor of 2 or a minus sign or a round off problem. But beyond that, I can't. On a written problem, I can. So if I can, and so what I'm going to be looking for is your set of decisions. I'm going to be looking at your diagram, possibly, to see how you see the problem. And you know, with me, it's always visual. Everything's visual, right? And so I grade people's diagrams, even if they're too small. If I can put my thumb over it and obscure your diagram, it's too small, and I'll grade you down for that. Because diagrams are important, especially if you're communicating with your boss. You know, any kind of graphic information like that, if it's too tiny, you know, it's going to look bad. It's not going to communicate. So all that stuff, Andrew, is what I'm looking for. I'm looking for your thought process, because especially if you don't have the right answer. So if the answer is, 26 newtons per coulomb for some electric field calculation, and all you write down is on your paper, right in the middle of the paper, 26 newtons per coulomb, you won't get full credit. And I'll show you the things that I'm going to be looking for. There'll be a little box down in the lower right showing the things that I'm going to be grading. So that'll be a little tip off, that I'll be checking. Like your acceleration and your stopping time, and then finally your stopping distance. For if I'm trying to do some kind of a, sliding calculation or something. Okay. So I'll have intermediate answers that I'm looking for, intermediate quantities, and I'll be looking for your thinking. So that's where the sentences and phrases come in. All right. And maybe an arrow or two to show the flow of your logic. All right. But numbers everywhere, So Andrew, you can't, scratch work is okay, and then write number 26 in the middle of the paper. That's not okay. All right. Clicking wise, it's okay, which is what we had for exam 1. So if I do written problems on exam 2, that's what we're going to be. It's kind of a higher standard, but yet it's a more forgiving standard as well. It's tougher yet more merciful. So, another question. Yes. Everything that we're going to be up in chapter, what is magnetism is 22, right? Yeah, that's what we're doing today. It's 22. So we're going to be somewhere in 22. So today's stuff and then Monday's stuff. So we're not going to be going into 23. And actually today I have a little bit of instruction from, I think, 22.9, just one diagram that I want to review with you. But yeah, Andrew's bringing up so actually today we're going to look at a picture from chapter 22.9, but mostly we're going to be up to 22.3 today. So we might do 22.4 on Monday. Forces. Okay. If there's no more questions about exam 2, let's get started with electromagnets. Now what we're going to do is can you help hand out? Come on up and get your electromagnetic kits. And we're going to do some simple. Actually, Andrew, you guys don't need flukes today. We don't need flukes. I juked you on the flukes. Right. Okay. Let's continue with our session. Now we've made some electromagnets and seen a little bit of electromagnetic field effects, and we use the compass to do that. Make a note: compasses are good detectors of magnetic field, especially the direction. And it's hard to tell the strength with just a compass, but with direction, yeah, you can do pretty good. Now we're going to do an alphanumeric question on your clicker. So go ahead and swap over. And now this one is by way of being a public opinion poll. So I'm going to give everybody correct answers. I want you to give me your best guess. For this layout, current going in that direction. Oh, this is wrong. Hold on. Okay, so here's your question. In what direction is the magnetic field at point S? Now, point S is over here on the right. The red is the wire, and I shows the direction of the current. Now, if you didn't denote the direction of the current in your experiment just a few minutes ago, you're a little bit out to lunch on this. This is the overhead view. So your field point is up, so your wire is like along the top of this monitor here, okay? And your field point is directly above it. The current's going in this direction. So go ahead and answer that. Type in a letter A, B, C, D, or E, and hit the send key. Also, make a diagram of this in your notes. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Cyrus Beckstein, are you here today? He's at the top of my list of mugshots here, the bees. Jenna Bailey's here, I think. Jenna, where are you at? She's not here. There's a lot of people absent. Okay, let's take a look at the answers that you guys have. Okay, now it looks like everybody chose, or a good number of people chose to the left. Some of you chose up, and some of you chose down, and some of you chose to the right. Now the problem with that is that it is wrong. The correct answer is this direction. So make a note of that. Now everybody's gonna, you're all get a point for that, so don't worry about that. But now let's take a look at the actual, and I was hoping that this would be more obvious with our little compasses and stuff, but it wasn't. So that was a public opinion survey. Now here's the theory. All right, and in image A, the first half, and this is from 22.9, figure 1. This should actually be the very first image in the chapter on magnetism, but it isn't. The current is going uphill. All right. So sorry, my cursor. We couldn't figure out how to make my cursor big, but my cursor is over here. See, this is like the point. What was it? Point S. Point S right here. Okay, above, and this little compass image here tells you the direction of the field lines. In fact, the field, or the magnetic field, the field line forms circles around this wire, right? So magnetic field lines are never like porcupines. They're always loops, like dipole fields. All right, so this is kind of a slightly different view of a wire. And this is the conventional current. So the electrons are actually moving from top to bottom. Okay. Now, on the image B over here, it shows RHR2. That's right-hand rule number 2. All right, now this is the right-hand rule, not for torque and angular momentum and angular velocity. That's from Physics 1. The right-hand rule for magnetism is this. You take your thumb of your right hand and put it in the direction of the conventional current, and then your fingers of your right hand curl around the wire in the same sense that the magnetic field lines do. Now, the field lines for a straight wire are all in the same plane. So those ones, it's kind of hard to tell here, but all 3 of those circles are in a plane perpendicular to the wire. All right, now if you have a bend in the wire or something, it's going to be different. It requires a lot of trig and a lot. And by the way, the calculus level for this would cause Andrew over here to burn his book and run home to mama. Get a little bit of get some pancakes or something. You know, it caused a lot of mental anguish. That Ampere's law. It's very tricky. But you know, but it boils down to the right-hand rule. So if you're in a, you know, and it works for circuits too. If you have a circuit and the current's going this way, then you use the right-hand rule to figure out, you know, where the field lines are going around that circuit. And a lot of times the field lines are going from all directions in a current loop. If you have so look at this. If my current, Alexandra, is going this way, and my wire is up here, so my wire's up here, so my current's going this way. So my field lines below the wire are towards me. That's what my fingers. Now, if my current in this side of the loop, the up, you know, this side, okay, so the current's going this way, it's going this way up here, it's going this way over here, right? And in the interior, the field lines are going towards me, right? Now, if I go over here to this side of the wire loop, the current's going down over here, and the field lines inside the loop are coming towards me. Now, if I go to the bottom where the current's going back this way, all right, the field lines inside the loop are, so inside of a loop, the field lines all point in one direction, right? They come, if you're going around counterclockwise, they're coming towards you. If your current loop is going clockwise, this is clockwise for me, the field lines are going away from me by this right-hand rule. All right. Now, another thing I want to emphasize with this, and I believe this is a concept from chapter 22.9. So dip ahead to figure 1 and read around a little bit in that. That's a little bit beyond what I asked you to read last night, but I did annotate it earlier, I think last night. Moving charge is the source of the magnetic field. And it is for this reason that we now know that electrical effects and magnetic effects are unified. Now, they figured this out in the 1800s. You know, they basically had a guy named Christian Ørsted. I think he was from Denmark. And he was setting up his lecture to demonstrate electrical currents. And he had a compass there, and he had some amps going through that wire, all right, from batteries. And he noticed that when he connected the current, or connected the circuit and the wire, and the current flowed through the wire, that his compass needle would jump, same as it did for us. All right, and so he's the one that discovered this effect. And then other people figured out all the calculus. So over the next 80 years after Oersted. We figured out all this stuff and why the right-hand rule works and stuff like that. But it is a fact. We now know that electrical and magnetic forces derive from electrical charge. The static part is what we studied with dipoles and electrons and stuff. The magnetic part is what we get from moving charges. So the moving charge is the source of the magnetic field. And I don't care. See, this is nice. Andrews didn't know this, but this is his graduate course in electrodynamics. This is a textbook, or one of the textbooks for it. And I'm sure they have in here something called Maxwell's equations, buku high-level calculus, enough to choke a mule. All right? And in that is the assumption, among other things, that the source of the magnetic field is a current of charge from point A to point B. And if you know where it's going, you know where the magnetic field lines are going. All right, now, in general, this is something that we know from previous studies. The electric field lines are like a porcupine. So if you have a positive Q, the field lines go outward like a porcupine quill. All right, and if you have a negatory, they go inward. So that's the reverse or the anti-porcupine effect. All right. However, this is not ever observed with magnetic field lines. You never ever. We sometimes think that some of our physical theories ask us to look for a magnetic charge that's all south, no north, or all north and no south. But so far, the only thing that we can see in nature is dipole level or higher. All right. So a dipole field, we know that what that looks like for two positive static charges, or for a positive and a negative static charge. This is what it looks like for a bar magnet on the right and a coil on the left. Now that coil is a good example, and those little black things are iron filings. If you've never done that in like 5th grade science, it's kind of cool to be able to do that. And I'll ask to see if they have that demonstration. Maybe we'll do that on Monday with bar magnets and stuff. But so the iron filings are little teeny shavings of iron from when people are sharpening knives and axes and blades and stuff. If you have a samurai blade, you got to keep it sharp, right? I mean, why have it if it's not sharp? So, and these are the little scraps left over from sharpening your blade, and then you get them, and they just line up, the little filaments. They form little lines, and it gives you an idea of the field lines. Now, those are the exact same field lines that we've seen for a dipole. But this is from moving charges. Now, you may say to me, Dr. B, that magnet is not charged. It's not connected to a circuit. The one on the left, image A, is implicitly, it's kind of a diagram of an electromagnet, basically a solenoid, a coil. And you can see how intense the field lines are inside the coils. And that is why you make an electromagnet, because you get very strong magnetic field lines. So remember, the density of the field lines is proportional to the strength of the field. So inside that coil on the left, you have really, really strong magnetic field. All right? And the iron bar magnet or steel bar magnet marked N and S that's actually got currents, but not a big macroscopic current. What we think is happening there is, and this is from chapter 22.2, figure 7, we think it's either electrons orbiting the atom or the electron spin. And so, and you get field lines from either of those. And what they're doing with that image on the right is like a travesty of physics, but it's in there. And I have a long annotation about it, basically getting cranky about that image because electrons, we don't really think that electrons have structure, and we've never found any structure. So thinking of them as little spinning objects like that, we don't really know how to describe that. But they do have intrinsic angular momentum and intrinsic spin. And in chemistry class, you have to deal with that all the time. Heisenberg uncertainty principle, plus up and down electrons, if you remember that. Did you guys do that in chemistry class? Up and down electrons and stuff? Yeah. Okay. So you could talk about it, but you can't really say, well, it's this little sphere, and the surface of the sphere has charge distributed on it, and therefore it's. Now, if we had a spinning, what do you call that? A Van de Graaff generator. The sphere of that has got charge distributed on it. If that were spinning, then you'd have a field like that, right? But we don't think electrons are like that. But we can. The electron still has a magnetic moment like this. And the other one is an electron definitely in motion. But even that is kind of deceptive because we don't think of the electrons anymore as orbiting the nucleus like a planet orbits the sun. It's an electron wave. Covalent bond. If you know anything about covalent bonding would never work with this model. Covalent bonding is a quantum mechanical effect, 100%. And so the quantum mechanical view of this is the electron behaves as a wave, not a little planet. But for basic understanding, it's still helpful to think of it in these terms. And this is what we think is happening with iron atoms. So the atomic scale, we ascribe the magnetic field to the motions of electrons and protons, mostly electrons. So iron atoms have this effect where the iron atom is like a little teeny electromagnet. And it's a lot like image A with, one or two electrons perfectly set up to magnetize everything around them. And so that's why iron is what we call ferromagnetic. So in my opinion, the whole order of chapter 22 is kind of reverse what it should be. You should start with electromagnets because that's what we found out first. We didn't know jack about atoms and stuff like this until 100 years later. So it's kind of reverse polarity there. But anyways, this is what we think is happening on the atomic scale. Did anybody see my annotation about the Liberty ship? Anybody read about that? You didn't? I should have asked some clicker questions about that today. All right. We'll go over that on Monday. Let's go to the dot cam. I want to show you some stuff about relativity relative to the stuff that we've talked about already today. So can you swap me over to the dot cam, please? Yeah, Andrew. What's that? Not all the way. Everything that I'll give you a formal list on Monday. Everything that we cover today and Monday. But so I think I was thinking it would be Andrew. I was thinking it would be mostly chapter 22.3, but I think we'll go a little bit further than that, maybe 22.4 on Monday. Okay. Andrew, could you dig out my blue pen from over here, please? All right. What's today, the 11th? All right. Now, I want you to draw a diagram of some electrons evenly spaced, but at rest. And I'm just going to space them across here. And I'm just going to eyeball this in. All right. Now, we know that each of these has porcupines. Okay, let me put a few more. The field lines are inward porcupines. All right. So, for instance, right here, there's a downward field line into this negative, into this electron here. All right, and we know that there's a field line here like that. All right. Now we know that there's a field line from this one that's kind of dipped over this way, and a field line from this one that's kind of dipped over this way. But now these two nearest neighbors, the net field from them is also upward down here, right? Now these two nearest, the next two neighbors out, same thing. They're going to contribute some upward electric field right here. So let's put for the total electric field, I'll use my blue ink. Let's put a field line that looks like that. All right. Now, I'm going to put some dots out here to the right to symbolize that it's infinite or really, 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 really long. And same dots over here to the left. All right. So what that means is that any of these field lines here are going to be, for any of these charges, you know, no matter where you are on the line, I'll just draw it 4. And by the same token, above, you're going to have downward field lines like this. Now, we're looking at this line of charges. They're static. So they're not moving. They're just kind of stuck in plexiglass or something. And so now I'm going to draw a perspective view. Now see if you can do this. Just watch what I'm doing. And I'm going to try to draw a perspective view with some minuses getting smaller and smaller in the distance. And I'll just go dot, dot, dot in that direction. And I'll go dot, dot, dot in this direction. Okay? Now, the field lines are going to be inward, like this. And that's above and below the plane. Now, if you go straight across, so here's where I'm doing my perspective. So let's say that these electrons are all flat on a table. Here's the tabletop. Okay. So there's my tabletop. And these field lines here are perpendicular to the tabletop. All right. But the field lines that are in the tabletop will be parallel to the tabletop and inward. All right. So if you look in the same thing over here, now I'll draw this a little bit smaller. And I'll just draw the stuff above the tabletop. All right. And down below, I'll draw the other one below as a dashed line. Okay, so there's two of them. So we do have this anti-porcupine effect, but in only 2 dimensions, not all 3 dimensions. If it was isolated negative charges, we'd have 3-dimensional anti-porcupine. The quill's coming inward. But this one, we just have it 2-dimensional in planes that are perpendicular to the line of charges. Okay, so in other words, these 4 field lines that I've drawn here form a plane that's perpendicular to the tabletop. So planes perpendicular to the tabletop. Also, okay, so that's a way. So that's a perspective view. So here's the perspective view down here, and here's the perspective view up here. Andrew, can you switch to the next document, Cam? Yeah, just hit the space bar. Okay. Now, at the bottom of this sketch, let's just write this sentence. You, the observer, are at rest with respect to the array of electrons. Okay. All right. So let's say that you're out, a few centimeters or a few nanometers away from the electrons, and these are the electric field lines that you'd map in. Now, emphasize this word, at rest. In other words, those electrons are not moving. Now, let's say, so for part 2, okay, so that's part 1. This is part 2. Say this. Say that you start moving at speed v, or at velocity v, so vector v, parallel to the line of charges. All right, now let's sketch that out. All right, so let me do, and I'll do this in perspective again, and I'll start with a big electron here, a little bit here, a little bit smaller, a little bit smaller. All right, now go ahead and sketch in the tabletop surface again, just for visual fiduciary purposes, in other words, for keeping your orientation, and draw in a vertical through that first electron, okay, so that we can visually orient our perception. Right now it's a 2-dimensional piece of paper, and we're trying to draw a 3-dimensional system. All right, now, I want you to put a dot out here at the edge. Can you give me my red marker? I'm going to make this in red. There should be a red one in there.
Okay.
Thank you. Yeah, the red. All right, so let's make this red. Okay, so this is you. You are here. But let's say that your velocity is, your v is in this direction. Okay, so there's your velocity. All right, so now in other words, you're a moving observer. Now, you're moving relative to the electron array. All right, so that's good. Now, let's take a second diagram and let's make another diagram of the electrons. So I'll start with a big one and then kind of move the smaller ones off here. Okay. So this is part 3. All right. Now, so go ahead and write trace a line through the electrons, just for bookkeeping purposes. All right. So there's your line, and draw on the tabletop, just for visual bookkeeping purposes. Okay. So there's my tabletop again, and draw on a vertical to the first electron. And again, put a dot here for you. That's where you are. You're still there. Now, in diagram 2 up here, the perspective is from the observer at rest with respect to the electrons. Now, what do you observe in front of you? When you're looking at those electrons, what directions are the electrons moving? I mean, they're going to have a speed and a velocity vector. What direction is it going to be? What's that? No, not northeast. That's what you're doing here with respect to the electrons. So you're moving this way to them. Yeah, so they're gonna. It's for you. They're gonna look like they're going southwest. So I'm gonna put a okay. So this is minus of the other v, exact opposite. All right. All right. So this v up here in number 2. Can you switch over to .cam image 3? All right, good, thank you. So this one in image 2 is V kind of going off to the northeast, to the right side of the tabletop. This one's going minus V, same speed but opposite direction to the left side of the tabletop from this view. All right, now. Electrons with a left, and we'll call that leftward, okay? Leftward motion of the electrons. Okay, so the electrons are moving to the left in this one. The opposite of your motion from the point of view of the electrons. Now, so number 2 and number 3. Hold on. I think I did it again. Okay, it's still recording. Good. So number 2 is from the point of view of the electrons. Number 3 here, Roman numeral 3, is from the point of view of the of you. This is from your point of view. You see the electrons moving off to the left. Now, what do you call that? You see a bunch of electrons moving in a certain direction. What do you call that? call it a current. All right? Um, what does a current generate? Wait a minute. What direction is the conventional current? The electrons are going to the left. What direction is the conventional current going? Okay, so conventional current, physical current is going to the left. Conventional current is rightward. Right? So now, what are you now able to observe in addition to current moving? What kind of a field can you now observe at your location? You're going to find a magnetic field. Therefore, you observe your compass needle picking up the magnetic field of the current. Okay, IQ test. At point U, for this current, what is the direction? Sketch in the magnetic field vector at point. So it's going to be some kind of an arrow with its tail at U, right? And it's going to be going in a certain direction. Now use the right hand rule. Your thumb points in the direction of the current. Okay. And figure out, okay, so point your thumb in the direction of the current. And then figure out, and you're going to have to draw it in perspective. All right. Carly Gonshak, do you have a sketch in yet? What do you think for this? Madeline, do you have a sketch? Who's got a sketch? Who's got a sketch? Who's got their vector sketched in? Raise your hand if you have a vector sketched in. You do? Of the magnetic field at point U. Don't be confused, use your right hand rule. Conventional current is where your thumb is. Your thumb is in the direction of the conventional current. So you're going to have to visualize it a little bit. Maria, do you have it? Who's got a notion for their magnetic field vector at point U? You are here. There's no depending about it. There's only one direction it's going to be. Go ahead and say that. Go ahead and stand up. Shahab Ishmael has something to say. Go ahead, stand up and say it. Stand up and say about the direction it's going to be, either one or the other.
Oh, well, I mean, depending on which way the current is flowing, it's either going to be up
Speak to the class and speak loudly.
Depending on the way the current flows, whether it's left or right, it'll change the magnetic field direction either up or down because of the right hand rule.
Okay, so Shahab Ishmael is saying, all right, it's up or down depending on the current. And that is correct. It's going to be up or down. So it's going to be parallel to this vertical axis here but its tail's going to be out here. But is it going to be up or is it going to be down? What is it? What does it have to be? Yeah, it's going to be downward. So go ahead and write a magnetic field vector down here. Now, you guys, the customary symbol for a magnetic field vector is the letter B, capital B. All right? Now, we're now at the point where I can tell you a story. And the story is this. Go ahead and switch over to the laptop. And I want you to listen very carefully. In the textbook, there's a section where they say that Einstein discovered the theory of relativity because of his childhood fascination with magnets. That is not true. He did have a childhood fascination with magnets. In his paper of 1905, and in his writings about it, he basically did what we just did. He said, what if you're, with this one exception, what if your speed, you're the observer, what if your speed is the speed of light? He said, think of yourself as being on a streetcar. So for him, that was in Vienna or Zurich or something like that. You know, back in the days of streetcars. And he said this, someone shines a light in the same direction as your streetcar. And you're in the streetcar. And if you're at rest, you just see a flashlight beaming straight down the street. But if you boost to the speed, if your streetcar, you've got a really nice streetcar, you can go at the speed of light. Pretty sweet. Better than Bumblebee. So if you boost your streetcar to the speed of light, then what do you see? Because you're traveling at the same speed as the flashlight beam. You know, and so you have an electromagnetic field propagating down the street at the speed of light, and you're propagating at the speed of light. So you're at rest with respect to the electromagnetic field, or are you? Now, we just went through this discussion, very similar, of a linear charge array of electrons. And if you're at rest, you don't measure any magnetic. Go ahead and make a note of that in sketch number 1. You don't get any magnetic field there. You're at rest. You got a bunch of electrons. You got some electric field lines, some anti-porcupine field lines, but only in planes perpendicular to the tabletop and perpendicular to the direction of the electron array. But you don't have any magnetic field because nothing's in motion. There's no charge in motion in the first diagram. Right? In the second diagram, you boost, and now the electrons, you're buzzing past the electrons. All right? Now, if you close all the windows in the streetcar, you're buzzing past this array of electrons. You don't know that you're in motion, but you do know that there's charges in motion because now your compasses sketch number 3, your compasses are going to pick up the magnetic field of that array of electrons that now appears to be in motion relative to you. And the same thing with Einstein's streetcar. That is what he was thinking. What does the observer see when he boosts up to the speed of light? What happens to light? Because light is going at the speed of light. And if you're also going, would you just see an electric field? Or do you only see a magnetic field? And do they oscillate? Because, electromagnetic fields, they oscillate. They have a frequency, everything like that. Now, Einstein's answer to that question, boosting that streetcar, just like us, it depends on what the observer sees. So those electrons, they're just, to themselves, the electrons, I don't see any magnetic field. But to an observer in motion with respect to the electrons, yeah, I see a magnetic field. Same thing with the speed of light in Einstein's streetcar. It depends on the relative state of motion. And that is why his answer to that very question, what does the observer see, that is the very heart of his theory of relativity. And that is what he was thinking of. He was probably thinking about magnets, during lunch down at the cafeteria. But when he was writing that paper, he was focused on this relative state of motion business and what that meant. And we now have an idea of what is behind that. Now, I'll give you a little hint of things to come. And this is something that I don't know if Andrew knows. It is possible to unify the magnetic and the electric fields into one coherent field. And did you do the Meyer tensor in electrodynamics? Did you ever hear of it? There's a way to transform the electric field and the magnetic field so that they're exactly equivalent. Now, right now, for us, the magnetic field is not equivalent to the electric field. Because, if you're static with respect to your charges, you don't get jack for magnetism. But if you're in motion, you do get magnetism and electrical field as well. Now, it's possible to change coordinates and stuff and get a totally unified field, but it's way past Andrew's level. It's way past your guys' level, but it is possible. All right. So I want you to remember. Now, I mentioned that in the annotations in chapter 22. So what I want you to do for the weekend is two things. Skim up to 22-9. Just skim. Look at the pictures and stuff, and something seems interesting, read about it a little bit. Definitely study 22-3, and definitely study 22-4. We'll definitely do that. Hold on, we're not dismissed yet. We're going to do some calculations from 22-4 on Monday. All right, so review that. Serious level of review. Also, we're going to have another homework assignment, homework 3, over the weekend. So be ready to do that and do that for Monday. Okay, now you're dismissed. What's that? Yeah, it's gonna be available till midnight Monday again. So I'll try to get it in today. Where do you work? Well, where's that? Really? So, down the research part? So you have to work all weekend? What do you? Is that a good paycheck? That's good. Let's get my cursor.